We spent a lot of time in this unit so far talking all about different ways that you can measure stars, galaxies, and other parts of our universe. Today we're going to pull it all together and talk about the fact that this is really all telling the same story, even though it's felt like random little pieces here and there. All of this can kind of be summarized with this question of pursuit where we're trying to figure out how far away things are when we look up at the night sky. So today we're going to overview a little bit of those different aspects and how they're all connected together. Just overall, this is the IB Physics data booklet for this particular unit. There are three subtopics here that we've been focusing on. The subtopic on stellar quantities, subtopic on stellar characteristics and evolution. Then on our last lesson, we talked about cosmology. We'll close up with a little cosmology today as well, talking about the distant past of our universe and then what the possible future might be. We'll also find in our data booklet some constants that are really important. Anytime you're expected to solve any of these problems, these constants are part of it. So we see light year, parsec, and astronomical units. Really, these are just conversions. So just like you would convert inches to centimeters, you can convert light years into meters, and vice versa. We've also used speed of light in a vacuum as part of this. That was actually part of our derivation of light year, to figure out how far away that actually is. So what I want to focus on here is what are these different ways that we've gone about measuring the universe? And specifically, the most interesting part of that for us is how far away these things are. Like we look at the night sky and it looks kind of like a two-dimensional painting, really, because everything is far. But it turns out that some of those points of light in the night sky are significantly farther than others. And normally we see depth because we have two eyes and our depth perception. Each eye has a slightly different view. Now we can't do that to see the depth of our universe, so we need other techniques. The first technique is actually pretty similar to that eye example. Parallax, we use the idea that if you take a measurement of the night sky from two different points in time, so specifically 6 months apart, January to July, or any 6-month gap, you're going to see a different night sky slightly for those more close to us stars, because January and July, we are as far away from where we were when we took the initial measurement as possible, because the Earth orbits the sun. So 6 months later, you are looking at that same star from a different point of view. And if that star is closer than the other stars in the night sky that are behind it, we see the locations, so that pink star there, jump back and forth. Kind of like if you were to close one eye, put out a thumb, and close out your other eye, you'll see your thumb move back and forth. Same thing with this star. Now we can use that and the angle that we are seeing this moving back and forth to actually calculate a distance. The relationship is that 1 over the angle in arc seconds will give us a distance in parsecs. Now parsec is just a unit of astronomical distance, and we can convert that into light years. We are provided that conversion factor, that 1 parsec is 3.26 light years. But then of course we'll probably have to convert light years into meters. You are not in the data booklet given parsec directly into meters, so you're going to have to go through light years in order to get to meters if you need to. So this first technique, parsecs, or parallax and parsecs to find distance, really only works if that star is closest to us. Our next circumference, or our next moving outward for stars, next farthest along, we can use Cepheid variables as what we call a standard candle. As a reminder, this type of star is a star that changes in its luminosity over time. It cycles in these periods of usually days. So here we have a magnitude that's showing its period repeats every 5.4 days. Now, it's been noticed that if you have a longer period, that star is also more luminous, that there's a relationship between how long it takes these stars to go through its brightness and dimming cycle versus how luminous it is. And if you know the period in days, you can figure out its rough luminosity. in terms of the sun, convert that into watts. Now, if you know the luminosity, exactly how much power a star is emitting, and you can measure its brightness up in the night sky from what's actually making it down to Earth, you have enough information to actually figure out its distance, because brightness is basically just the intensity of that star's light by the time it makes it to Earth. And the farther away that star is, the dimmer it's going to be by the time it gets here. Now, normally it's hard for us to figure out its original luminosity unless you're right there measuring the star. Here, we're able to use this interesting feature of Cepheid variables to figure out its luminosity. And once we know that luminosity and we know the brightness, we can rearrange and solve for the distance. So after parallax, Cepheid variables are our next way of measuring those next closest stars. We can use a similar technique to go out a little further. To do this, we're actually going to use our old friend, the HR diagram. Now, before we can do that, we have to use this relationship that says if you know the color of your star, so the maximum wavelength that's appearing, you're actually able to figure out its temperature in Kelvin, because as black bodies or things that are emitting radiation because of their high temperature are emitting that radiation, the hotter it gets, the lower that maximum wavelength is. It goes into the visible part of the spectrum, starting with red, and then as it gets all the colors, more of a white hot. Now, if we know the temperature of that star, the HR diagram helps us find some patterns in the different stars that exist. And specifically, what we're going to be looking at here is the main sequence. Most stars fall on this line somewhere. Now, if we know the temperature here is on the x-axis, we can figure out where that temperature lands in the main sequence. And we're going to do the same thing that we did with the variable stars in the last slide. If we know where it lands in the main sequence, we can follow that over and figure out its relative luminosity. And again, if we know the luminosity and we can measure the brightness here on Earth, all we need to do is plug it into this equation to figure out, okay, it's this bright here on Earth, but we know it's emitting this many watts. So how far away must it be that it is exactly this dim or this bright by the time it makes it to Earth? So in a very similar fashion, we can use an HR diagram to find the luminosity, use luminosity and brightness to find distance. Now, if we want to go even farther, we need to start using Hubble's law and redshift. As a reminder, redshift is the fact that, or the nature that if something is moving away from us, its light spectrum is going to be shifted towards the red part of that light. And the reason for that is similar to the Doppler effect with sound. If something moving away from you, the wavelength of that sound wave gets stretched out and the sound sounds lower. In terms of light, if something's moving away from you really fast, the wavelength gets stretched out, and the longer wavelengths in the visible part of the light spectrum are red. So what we'll see is these atomic spectra are shifted slightly from what we expect them to be, because we know the signature, the fingerprint of these different elements that make up the stars, and we know where we would expect to see them if the star wasn't moving, and they're not there. So they're just shifted over. We can use that shift, that change in the wavelength, to calculate roughly what the velocity is of that star or that galaxy moving away. Now, there's a relationship here as well. Hubble is famous for seeing this relationship that as the distance of the star or galaxy, is what he was really looking at, gets larger, so does that velocity, that recession velocity. That here distance is measured in megaparsecs and velocity is kilometers per second. And the farther away the galaxy is, the faster it's moving. And it was a fairly linear relationship, so use this equation that the velocity is just some constant times the distance. That constant is basically the slope of this line. We call it Hubble's constant. And the best measurements that we've had are closing in on a value around 70 kilometers per second per megaparsec. And this value is going to be really important for us as well. That means that if we can calculate the redshift, we can use this relationship and that value to figure out the missing variable. The missing variable is distance. So looking again at this chart, Parallax, Cepheid variables, HR diagrams, and Redshift are all different ways for us to measure distance. If we look at our night sky, everything looks like it's in the same spot at some dome above us, but they are all actually very, very different distances from each other. Something that you probably don't even think about. If you go look at the Big Dipper, those stars aren't anywhere near each other. They are offset, but since we are looking at it from our perspective, we see them all making one single picture. So let's look at this Hubble's constant one more time and use it to solve one of the most interesting questions that we can ask. How old is the universe? So if we look at this equation, that the velocity of a galaxy that's receding away from us is equal to Hubble's constant times the distance, and we know Hubble's constant, we can use that to do some tricky math here. We know that the velocity can be calculated just distance divided by time. And if I plug that in for this, I know that this also equals velocity, the Hubble's constant times distance. So then I get a relationship that Hubble's constant times distance is just equal to distance over time. That's just setting those two velocity equations together, which is something that we're allowed to do. I notice that distance shows up in both places here, so I'm going to cross that off, which means that the time, if I rearrange it, should just be 1 divided by Hubble's constant, this h naught value. Now that seems weirdly simple, so let's try it. Let's see what it gives us. If we do 1 over that Hubble's constant, 70 kilometers per second per megaparsec, we get this value of 0.0142 seconds megaparsecs per kilometer. Okay, what does that represent? That's a weird unit. And this equation tells us that it's time. That is technically a unit of time. And we see the seconds there, that kind of makes sense. But then we see these two other units. We see a megaparsec per kilometer. Megaparsec is a unit of distance, and kilometers is a unit of distance. So it's kind of like if you were saying like miles per meter. If you did some conversions, those two should cancel out. They're both distances. So we're going to do the ultimate dimensional analysis problem here to turn this into just seconds. If I start with that value, that's 0.0142 seconds times megaparsecs divided by kilometers, I can first convert this megaparsecs into parsecs. Megaparsecs is just a million parsecs. So I'll do that. That cancels out the megaparsec. So that would give us seconds times parsecs divided by kilometers. Then I can go parsecs into light years. We've seen that conversion done. That will cancel out parsecs. Then I have light years per kilometer. So I'm getting closer to something that's useful. Even closer still would be if I can take light years all the way to meters, which I can do. You're given that conversion that there's 9.46 times 10 to the 15th meters in every 1 light year. That cancels out light years. So now I'm left with meters per kilometer. So I'm really close here that if I add one more conversion factor with 1 kilometer on top, 1 meter on the bottom, I can cancel out meters. And then I'm left with kilometers on top, kilometers on the bottom. So the kilometers cancel out as well. So in that super satisfying chain of dimensional analysis, everything cancels except for seconds. If I plug that all in, I get 4.4 times 10 to the 17th seconds. Now, that is actually the age of our universe. Normally, you wouldn't talk about that in seconds. That feels like a weird unit to use. So let's convert that into years. We'll take that divided by 60 to get into minutes, divided by 60 again to get into hours, divided by 24 to get into days, divided by 365 to get into years, and we're left with about 13.8 billion years. So one of the reasons that finding a more and more accurate Hubble's constant is important to us is that as we refine this number, as we get better and better measurements to figure out how our universe is expanding and moving away from us, we can work backwards and actually find a more and more exact estimate of our universe's age. So right now, our best estimate is somewhere around 13.8 billion years.